Hello, everybody, and welcome back to AP Chemistry. We're taking a look at Chapter 3, Section 3. And don't be fooled, folks. The name stoichiometry looks really intimidating and everything, but really, this word of stoichiometry just means a systematic way of converting from one thing into another. We do that through the periodic table, we do that through a balanced equation. So, we're going to go through some examples of stoichiometry. This is something that we do within Gen Chem as well. So before we get going on the true chemistry aspect of things, let's take a look at some examples of what this might look like within just a general overall world. And so we can use this system of going about and figuring out amounts of things and converting from one thing into another just through a common everyday type of experience. So in the construction of a car, one body plus four tires will make a car. One body weighs 1,250 pounds, one tire is 45 pounds, one car weighs 1,430 pounds. And so basically what I'm giving you is a whole bunch of different conversions along the way, some factoids, if you will. And so we can go through and we can answer a whole bunch of different questions from this particular set of information. Now, what we need to realize with this, again, this is related to chemistry, but what we need to realize with this is actually the formula for basically a chemical equation. We have one body plus four tires. That will make as a product one car. So if you will, these are going to be my reactants, and this is going to be my product. Okay, so I have some information about each of those individual things, but really along the way, I'm going to be able to take a look and use this information to arrive at my answer. And notice I said that, we're arriving at our answer. So let's take a look at this first question. It's saying 900 pounds of tires. I want to know how many cars I can get from that. Well, if I have 900 pounds of tires, I need to answer the question, how many cars can I get from that? Well, what do we remember? I'm going to get rid of the label tires and I'm going to get it into cars. Okay? Remember that one car requires four tires. Okay? So that's what we've got there, but you'll notice I can't really go directly from pounds of tires into tires themselves. I need to convert. And so there's a bit of missing information because there's pounds of tires versus a number. All right, so here's what we want to do with this. Rather than make this all complex, I simply just write down what I've got and get rid of units. So I have 900 pounds of tires, and I need to get rid of the label pounds of tires. Now, what do I know about tires? Each tire has 45 pounds. So I can go from pounds of tires into number of tires, and then I can go from the number of tires to figure out how many number of cars I can get. What do I know? One car has four tires, and one tire has a mass of 45 pounds. Okay, so from there, I know if I just run my math, I can get 5 cars from this. Okay, so watch your labels with it, and I'm going to be demonstrating each one along the way so you can see how this is going to work for us. Okay, next one we're going to be taking a look at the mass of cars that can be built with 900 pounds of tires. Notice the question is similar. I still have 900 pounds of tires, but instead of how many cars, I want to know what's the mass of cars. So let's go from pounds of tires to number of tires. And then I can say the number of tires to the number of cars. But I have one more piece to this, and I'm asking the question, what mass of cars? So then I can go from number of cars to pounds of cars. So it starts out the same. One tire has 45 pounds to it. I say that one car has four tires, and one car now has a weight of 1,430 pounds. Okay, in doing that, I end up with an answer of 7,150 pounds of cars. Okay, just keeping in with my process behind it all is the biggest key to everything. All right, so let's take a look at another one. I want to know how many pounds of tires if 8,750 pounds of bodies are used. So it's kind of a weird, convoluted question. And sometimes chemistry is that way too. It's like, I'm not quite sure what they're getting at, but I do know that I've got 8,750 pounds of bodies used to build the cars, and I want to know how many pounds of tires are needed. So I'm not looking at pounds of cars, I'm looking at pounds of bodies. What do I know about that? One body then, let's see, one body has 1,250 pounds. So I can go from pounds of bodies to number of bodies. I can then get rid of the label number of bodies, and then I can get to, since I'm headed toward tires, I ask the question, how many tires are needed? And then I can say, okay, now that I know the number of tires, I can then go into number of pounds. Okay, so then I see if I have one body, we had 1,250 pounds. I say that one body does still require 4 tires. And then I can go through and say one tire is 45 pounds. Okay, so in that process, I end up with 1,260 pounds of tires. So you see how this process works. Just showing your work along the way. Avoid what I call chicken scratch math. You're not going to be able to just show a number on the AP exam. You're going to have to be able to show your work of how you got it. That also saves you in the long run, because if you do a little dumb math mistake, like I always make, then you're going to find that the process was correct, so you're fine. All right, so finally we've got two things, and this introduces a new concept. So let me put the equation back on the board. We had one body, and we had 4 tires. That's going to make one car, isn't it? Well, here in this problem, this is a little bit more complex because I still want to know how many pounds of cars. I still need to know this. But now I'm given this many bodies and I'm given this many pounds of tires. So I have to do the problem twice. I solve it simultaneously. Let me do the pounds of bodies first. 18,750 pounds of bodies. And I want to know how many pounds of cars I can get, because that's ultimately what I want to do. So I can go pounds of bodies to number of bodies, and then I can go number of bodies to number of cars. Now, I'm not done because ultimately the question asked for pounds of cars. So we're going to go number of cars to pounds of cars. Okay, so now I can go through and say that one body was 1,250 pounds. I can say that one car needs one body, and one car has an ending mass of 1,430 pounds. So the number I end up here, if it was up to the number of bodies, it would end up being 21,450 pounds of cars. Okay, that's if it was up to the bodies. Now let's take a look and solve the problem and look at the tires. I have 1,980 pounds of tires, and I'm going to ask the same question. How many pounds of cars will that make? Well, my pounds of tires to number of tires, my number of tires to number of cars, and lastly, my number of cars to pounds of cars. So notice we're ending in the same place because that's what the question is asking. So I say one tire is 45 pounds. I say one car needs 4 tires, and one car has a mass of 1,430. So if it was up to my tires then, I end up with 15,730 pounds of cars. So what does this tell me? If it was up to my body, I would get 21,000. If I was up to my tires, I can get 15,000. In other words, this is what I would call my limiting reagent. I ran out of my tires. And so that's limiting my product. We refer to this then as my excess reagent. Okay, so the limiting will truly do what it says. It's going to limit my product. Okay, so this is a common everyday application with basically anything that we do in production and anything that with those regards. Now let's bring it to chemistry. Okay, we're taking a look at the problem note sheet number 1. Now, the same dilemma. I'm given a bit of information, and I'm given some information about that particular compound or whatever, but I need to start with an equation, and it needs to be balanced. So the solid lithium hydroxide used to remove carbon dioxide will form solid carbonate and liquid water. So lithium is a +1 element, hydroxide is a -1. I see that we're going to be removing carbon dioxide, and I'm going to be forming lithium carbonate. Carbonate is CO3 with a -2 charge, so lithium is still a +1, and I'm going to get liquid water. Now, before I can do this, that's just sketching out what I've got, but I need to balance. I can sometimes balance water easier by thinking of water as HOH. So I have one hydroxide, I've got one hydroxide. However, I've got two lithium, so I need two lithiums, which doubles my hydroxide. Okay? So now I see that I've got two waters, two hydrogens, as well as two hydroxides. Okay? And let's see, what else do I have here? I've got one carbonate, and we've got this problem with carbon dioxide and carbonate. Okay, so looking at this equation, it kind of fell apart. So let's reset the system here. And this is one of the frustrating things that I know a lot of people do kind of have an issue with when we're writing and balancing equations. Okay, so let's just go back, keep our wits about us. We balanced everything out okay, and let's look at this through another light. If we look at it this way, I see I've got the same issue of two lithiums. Okay, now this means that I've got two oxygens and two hydrogens, and I've got the two hydrogens here, but don't neglect these oxygens here. I actually have 2 plus another 2, which is 4 oxygens. Here's my 3 oxygens plus one more. Now I've got 4 oxygens. Oh, so it's balanced. I've got one carbon here. I've got one carbon here. So sometimes we got to play back and forth a little bit. I didn't need to use this trick. Okay, so we got a balanced equation. Cool. Let's move on to the actual stoichiometry of the problem. I'm looking for the mass of carbon dioxide that can be absorbed. So I'm looking for this. And if I have 1 kilogram, 1.00 kilograms of lithium hydroxide, cool, I can just go from this into this. All right, so let's go 1.00 kilograms of my lithium hydroxide. And remember, you can't convert from anything into anything else unless we're in grams. So let's get rid of kilograms of lithium hydroxide and get it into grams of lithium hydroxide. Now let's go grams of lithium hydroxide to the moles of lithium hydroxide. In chemistry, everything revolves around the mole. Now, here's the deal. I'm going to be moving from one thing into the other. I can do that through the mole. Lithium hydroxide, I can go to moles of carbon dioxide because that's where I'm going. And the problem asked about grams or mass, so I'll just leave it in grams. I could go to kilograms if I wanted. And let's go from moles of carbon dioxide into grams of carbon dioxide. So the problem is done. I know that I'm in my target. This is stoichiometry. So if I look, 1 kilogram is 1,000 grams. I look on the periodic table for my formula mass, and I see that one lithium hydroxide has a mass of 23.95 grams. I see in my balanced equation, I have 2 lithium hydroxides for every 1 carbon dioxide. 1 mole of carbon dioxide is going to be 44 grams. I end up with an answer of 918.58 grams, and I'm done. Okay, so that's just that problem in working with one of the reagents and solving for the other. Okay, now it gets a little bit more complex, as we saw in our very last sample problem. What if I have all these other things going on here? Okay, we have a homecoming dance coming up. All right, so let's take a look at an example like that. So to take a look at that, I've got a bunch of girls, I've got a bunch of boys, and we're just going to be saying that a couple, one girl, plus, notice she's got a little halo, one boy, that will equal one couple. Okay, so it's a lame example with that, but let's take a look at the maximum number of couples we can get from this. Notice I've got 2 components, don't I? I've got a mass of girls, and I've got a mass of boys, okay? I've got that many pounds worth of each. And so the question is, how many couples can I get out of this? So let's take a look at the girl side. I have 9,375 pounds of girls. Okay. So the question is, if I go from pounds of girls into just girls, that'll give me a number. And remember, if I'm taking a look at a couple, well, a couple requires one girl. It's a 1-to-1 ratio. I take a look, I see one girl. The average weight of a girl is going to be 125 pounds. This is not a social statement. If you don't, it's a made-up problem. Relax. Now, we take a look at this problem, and I see that this will actually give me 75 females. Now, let's take a look at the male side. Okay, so we see that in this problem, we have 14,760 pounds of boys. Okay? Well, what do I know? That pounds of boys, I can figure out how many boys that would be. And then I say, okay, so of the boys, okay, I need to know how many couples. So I go back to my balanced equation, if you will. One couple requires one boy. One boy has an average weight of 180 pounds in this case. And so I would find that if it were up to the boys, I would have 82 couples. I should say couples in this case, not females. This would be couples. Okay? So what are we running out of? We're running out of females. I would end up with only 75 couples. Okay? Now, the question here, how much excess remains? Well, if I have only 75 couples, notice that if I have a difference here, I'll do the work up top. I can, if it was up to the boys, have 82 couples. If it was up to the girls, I'd have 75 couples. So we're talking a differential. We're talking a differential of 7 couples. So how much is left over? Who is my leftover? This is going to be my limiting. Here's my excess reagent. All right, so the question is, of those 7 couples, how many boys would that be? If they're taking a look at the maximum number of couples, how many would be left over? Is that couples? What is that? Well, let's go from couples to boys. Okay, he's my excess. And I saw that was a 1-to-1 ratio. I end up with 7 boys left over. Okay, they'll live. All right, so there is our scenario, again, putting the concept of limiting reagents in there. So let's take a look at one last problem. Okay, you have 3, or actually not one last problem, we got a couple more to go. We have one, now we're back into the chemistry world. We have 130 grams of zinc, and we get hydrogen chloride off of this. So we got to start with a balanced equation. Okay, so I'm taking a look, and I've got zinc. Zinc is by itself, it's not a diatomic element. I have hydrogen chloride, hydrochloric acid. Okay, hydrogen is a +1, chlorine is a -1. But this is going to be replacing, that hydrogen is going to be kicked out, and it's going to form a compound. The zinc will form a compound with chlorine. Zinc is a +2 element, and chlorine is a -1. Hydrogen is kicked out by itself, and it is one of those diatomic elements. I call them the Cliff Hobarts, which just simply means there are certain elements out there that exist diatomically. When they're by themselves, there's always 2. You guys are familiar with oxygen always being written as O2, but these are all the elements. We need to know that because that affects how we balance the equation. Now I'm balanced. So if I have 130 grams of zinc, the question ultimately is how much hydrogen or how much zinc chloride can be produced. Okay, so let's convert that ultimately, grams of zinc. Let's go to moles of zinc. And then I can go moles of zinc into moles of zinc chloride. And since the problem is saying the amount that could be in mass, let's convert that all the way down to grams. Amount could be left in moles, so look to your prompt. Either one would work. Notice I now have a grams of zinc chloride left. All right, so the problem will tell us how far we need to go with it, but this particular one, let's bring it down to grams. 1 mole is 136.4 grams of zinc chloride. I see in my balanced equation it's a 1-to-1 ratio, and then 1 mole of zinc is a 65.4 grams. All right, so if I do my math with this, I end up with 271 grams of zinc chloride. Now let's take a look at the hydrogen chloride end of things before I move on. I take a look and I've got 100 grams of hydrogen chloride. So I'm going to convert from hydrogen chloride to moles of hydrogen chloride. Then I go from moles of hydrogen chloride to moles of my zinc chloride, which is what they're looking for. And let's finish it off by going moles of zinc chloride to grams of zinc chloride. Okay, so 1 mole is 136.4 grams, but this time I have 2 moles of hydrochloric acid to 1 mole of chlorine. And then 1 mole of hydrochloric acid, hydrogen is 1, this is 35.5, so it gives me 36.5 grams. So if it was up to my hydrochloric acid or hydrogen chloride, I would end up with a mass of 187 grams of zinc chloride. Now this is the cool part. It was a lot of work to do, but what did I just do? I said that I was going to run out of my hydrochloric acid. It's only going to give me 187. I ran out. This is my excess reagent. And now I can answer part B. I have to identify who my excess is. You can't tell until you do the math first. I can only get this much, so all you have to do is circle it. And so now, to figure out how much excess remains, let's take the difference between the two. And so the difference between the two potentials ends up being an 83.9 grams of zinc chloride difference. And the question is, if I have that much difference, how much excess does that make? So the difference between the two products is this many grams of zinc chloride. Let's go back and solve it for my excess. So let's go grams of zinc chloride to moles of zinc chloride. And notice I'm simply going to follow this equation backwards. I'm going to go moles of zinc chloride to moles of my excess. In this case, that was zinc. And then I can go moles of zinc to grams of zinc. Okay, so no real thinking here because all the thinking and searching is done for masses and all that fun stuff. This was a 1-to-1 ratio, and I can just copy down from the problem up above these things. What does this tell me? This tells me that I end up with 40.2 grams of zinc remain. So I just worked the problem backwards for that once I've taken the difference between these two potentials. Okay, so this one's going to be our last problem, okay? Taking a look at the different examples of what we got, let's take a look at one more. Nitrogen gas can be prepared by passing it through. So it's going to be prepared by passing ammonia over solid copper oxide. In other words, what we're going to get is ammonia over your copper 2 oxide. That will give me my nitrogen gas. Okay, nitrogen's a gas there. Now the rest of the problem is saying that I'm going to be getting solid copper and water vapor. So there's my solid copper. It's not diatomic, so I don't double it, and I get water. So looking at balancing this, it's a little bit different. Let's look at my hydrogens first. On this side I see 3, on this side I see 2. So let me get that evened out. I see I've got 2 nitrogens, 1 copper, 1 oxygen, 1 oxygen. That served me well. So the question is, the other products are going to be this. We see that we have this many grams of ammonia. We have this many grams of copper oxide. Which is the limiting reagent? Now, here's the trick, guys. Don't answer that question yet. I look to the end and say, oh, they're ultimately asking for this. So let's just solve for that. Okay? And so I need to set it up just like before. If it was up to my ammonia, I have 18.1 grams of ammonia. Let's solve that for nitrogen now. Grams of ammonia to moles of ammonia. Then I can go moles of ammonia into moles of my nitrogen. Then I can go, because the problem asked for it, how many grams, let's bring this down to moles of ammonia, nitrogen into grams of nitrogen. Okay, formula mass of nitrogen is 14. We got to double it, so that's 28. My balanced equation, I see I have, we're going 2 ammonias to 1 nitrogen. So 2 ammonias to 1 nitrogen. And 1 mole of ammonia, 14 plus 3, that's 17 grams. And so I end up in this case with a mass of 14.88 grams of ammonia if it was up to ammonia, or grams of nitrogen if it was up to grams of ammonia. Let's take a look at what it would be if it was up to copper oxide now. I have 90.4 grams of copper oxide. I can't just look at and know automatically. So let's solve for the math. Let's do this and let the numbers tell us which one we run out of. So I'm going to go from moles of copper oxide to moles of nitrogen again. And then I can go moles of nitrogen into grams of nitrogen. Once again, 1 mole is 28 grams. Looking at the balanced equation, one of these to one of these now. And lastly, I see 1 mole of copper oxide. Copper is one we're going to use 63.5 plus my oxygen. So I'm going to end up formula mass for my copper oxide being somewhere around 79.55. Okay, so keep that a little bit further on. And I end up, if it was up to my copper oxide, I'm going to get 10.6 grams of nitrogen. So I run out at that point. I've run out of my copper oxide. This is my limiting reagent. This is my excess reagent. Okay, and you can simply just label it. Remember, the first question was asking which is. So you can label it this way, you're good to go. Now look at this third question though. This third question is asking something slightly different. And it asks, if 6.6 grams of nitrogen are formed, what's the percent yield? Okay, percent yield is a little bit different. Percent yield is how good is this process? Percent yield is a process of taking a look at what you actually get versus what you should calculate, what we call the theoretical. Now, we just did a whole bunch of math. This is theoretical. This is theoretical too. But that was according to the math. That's my theoretical value. This is telling me we actually got this. Now I'm going to have to multiply this by 100%, so that's fine. We're going to turn it into a percent. But what this problem is asking is actually quite simple. My percent yield is nothing more than saying if I only get 6.6 grams, but theoretically I get 10.6 grams, and I multiply that by 100%, I end up with a 62.5% yield. It means I'm only 62.5% efficient in the process. Welcome to chemical engineering. This is what chemical engineers do. They take a look and see, how can I make this process more efficient? And maybe it's just tweaking one thing or whatever. Maybe the process isn't very efficient at all. Okay, so that's all we're doing for this particular chapter. I know stoichiometry can sound intimidating. I know it looks like there's a whole lot of steps and everything, but honestly, when we take a look at these types of problems, it's just keeping your wits about you, making sure that we're doing the steps that are involved, and you really shouldn't have any issues once we get past getting into just, I guess, the common everyday stuff of calculations along the way. Okay, you should be finding you have some pretty good luck, and I wish you guys all the best.